All right, so now we're going to talk about the rates of these SN2 reactions and what causes them to be a fast reaction versus a slow reaction, etc. And again, what's an SN2 reaction? It's this nucleophile is replacing a halogen on a carbon skeleton. And why does that happen? Well, Cl- is really stable by itself. We're going to talk more about that soon, but we know that HCl is a really strong acid. That tells us that Cl- is really a stable, weak conjugate base. If we can understand that there's a partial positive here, a partial negative here, we can understand that negatives flow to positives, right? The positive pole of a magnet is attracted to the negative pole, so negatives go to positives. The negative here is going to be attracted to that positive charge on that carbon. But if we had different nucleophiles, we need to be able to kind of rate them as far as like how reactive they're going to be in this type of reaction. So which nucleophile will lead to the fastest reaction? Well, a stronger nucleophile, so that would be a more reactive nucleophile, will lead to a faster SN2 reaction. But how do we determine the nucleophile strength? So what do nucleophiles love? And you should maybe pause it and see if you can fill in some of these blanks on your own. Because it should be somewhat intuitive. We've been kind of developing this chemical intuition based on our acid-base chemistry and all these different concepts we've gone through. So this should be really related to a lot of that stuff. So pause it, try and fill in some of these blanks, and then come back. All right, you did that. You got a lot of them. Nucleophiles love nuclei. Which are positive charges, right? They love positive charges. They love positive charges because they're negative. They donate electrons. So they donate negative charge. So how is that related to bases? Well, bases love protons. And protons are essentially H+, right? They're H+. HCl is a super strong acid, and that's because that H is connected to that super electronegative chlorine that's trying to steal all the electrons for itself. And that makes the H really positively charged. So bases love protons, we'll say H+, which are positively charged. I'm just doing multiple positives there. And bases, to get that proton, they give up electrons, right? That's the definition of a Lewis base, an electron donor. Also, a Bronsted base is a proton acceptor, and to accept that proton, it has to give up electrons. So bases donate electrons. And again, electrons are negatively charged, so we'll put a negative charge there. So what you can kind of see here is that nucleophiles and bases, they're kind of the same thing, right? So if you already understand from the acid-base chapter what makes a really strong base, it's the same thing that makes a strong nucleophile. Nucleophilic strength is proportional. So that means if the nucleophile is stronger, it's also a stronger base. That's what proportional means. Nucleophile strength is proportional to base strength. So as we would say, that's a stronger base. That also means that it would be a stronger nucleophile. Blank acid means we have a stronger, more reactive conjugate base nucleophile. So would this be stronger that would fit in there or weaker? So maybe pause the video, think about that, and then unpause to figure it out. More reactive base, stronger nucleophile. We have a stronger nucleophile. It came from blank conjugate acid. So you've already paused it. You've done your blanks. The weaker acid has a stronger, more reactive conjugate base. That's straight from that conjugate base acid relationship that we learned about in the acid-base chapter. A more reactive base, so if we have a really strong base, it really wants that proton. And if it grabs that proton, it's going to make a weak conjugate acid. So let's look at that relationship. We think about a really strong base. The strongest base on our pKa chart would be CH3 minus. It's super reactive. Carbon does not want to have that negative charge. If there's an acid around, we're just going to put H plus. It would grab that H plus and make CH4. CH4. And how strong of an acid is CH4? It has a pKa of 50. So it's a super weak acid. It's a weak acid, so it's a strong reactive conjugate base / nucleophile. This is a strong base, a strong nucleophile. This base is really strong, which means it has a weak conjugate acid. So we can kind of look at it in both ways, and we'll do some practices on the next one. So now we're going to work on that idea of what is going to make a faster SN2 reaction. Remember, we have a stronger nucleophile that's going to lead to a faster SN2 reaction. So we have two different reactions here, A and B, same alkyl halide, different nucleophile. We have NH2 minus versus NH3, which is going to be the faster reaction. So take a minute to decide for yourself and maybe write yourself a small explanation. Just writing things out in your own words can be such a good way to kind of lock it in, create the knowledge for yourself. So give that a shot and then unpause. So boop, you did it. All right, so which of these is a stronger nucleophile? So nucleophiles are proportional to base strength. So which of these is a stronger base? Well, let's look at their conjugate acid. So we have NH3 is the conjugate acid of this. So this is the conjugate acid. The conjugate acid of this is, is NH4 plus. So which of these is the stronger acid? Well, we actually have pKa's for both of these on our chart. pKa of NH4 is 9. The pKa of NH3 is 38. So this is the stronger acid. So this is a weaker nucleophile. NH3 is a weaker nucleophile, weaker base than NH2 minus. So this is the weaker nucleophile. It's going to be a slower reaction. So A is the faster reaction. It has this nucleophile, which is a lot stronger. Another way that we can kind of see this is when we have two of the same element, nitrogen versus nitrogen, what are nucleophiles charged? Nucleophiles are negatively charged. They want positive protons. They're attracted to positive protons. So if we have the same element, nitrogen versus nitrogen, the one that's negatively charged is more nucleophilic. It has more electron density. So for those reasons, A would be the stronger nucleophile. All right, what about this one? Well, we have, again, same type of alkyl halide versus two different nucleophiles. And those nucleophiles, both, at first glance, looks like they have oxygen as a negative charge. So we can't really go off of the which one's more negative at first glance because they're both have a negative charge on one oxygen. But are either of these charges actually less localized? So yeah, are either of them less localized on a specific spot, or either of them delocalized? So because if the negative charge is more spread out, it's going to be less reactive because delocalization is a stabilizing factor. So yeah, one of them has something that delocalizes it, resonance, right? So this nucleophile down here, we remember that it's right next to the other pi bond, allowing for multiple resonance structures. So essentially, the negative charge isn't just on that oxygen, but it's also on this oxygen. So this is a delocalized negative charge. That makes it more stable So if it's more stable, what does that mean about its nucleophilic strength? It means it's less nucleophilic. So this one's more spread out, less nucleophilic. This is the stronger nucleophile, so that would be A, the faster reaction. We can also see we could have done that one the same way we did the first one, looking at the pKa's of the conjugate acids. So, and that way will kind of never fail. So you can always kind of fall back on that. So the conjugate acid of that nucleophile is this. The pKa value that we have for alcohols is 16. The conjugate acid of this guy is this one, and we actually know this one too. This pKa is 5. So this is the stronger acid making the weaker base, weaker nucleophile. This is the weaker acid, so this is the stronger base, stronger nucleophile. So this is going to be the faster reaction A. So yeah. All right, so now we have another one where we're looking at which is the stronger nucleophile. And again, stronger nucleophile means stronger base. Stronger base means it's the more reactive base. So which of these is more reactive, N minus or O minus? So we can go back to our qualitative understanding of stability. So is this negative charge more stable or is this negative charge more stable? So think about that for a second. Pause it. Decide for yourself. Is this one more stable or is that one more stable? Boop. All right, you already unpaused it. This is the more stable negative charge because it's on oxygen, a more electronegative element. So this is a more stable negative charge because it's on oxygen. So that being said, more stable means less reactive. This is the stronger nucleophile. This is the stronger nucleophile. Stronger nucleophile. So a lot of ways of kind of going about these. Again, we could go on the pKa method. What's the conjugate acid of this? It's that with a pKa of what? You guys should know all of them. pKa of 16. What's the conjugate acid of this? It would be NH2. So it's neutral nitrogen. That's most similar to NH3, right? It's nitrogen with 3 bonds and a lone pair. Both of these are the same in that way. And when you have nitrogen with 3 bonds and 1 lone pair, it has a pKa close to 38. So again, stronger acid, stronger acid, more stable conjugate base. Weaker acid, more reactive conjugate base. So this is the stronger nucleophile. This reaction is going to be the faster SN2 reaction. So, yeah, and on the bottom of your note page, it says that if leaving groups are identical, then nucleophile strength will determine the rate of the reaction, which is faster or slower. So these are identical leaving groups, stronger nucleophile, so B would be a faster reaction. And now we're moving on to looking at leaving group strength. So leaving group is the chlorine, and we'll talk about that coming up.